Hi, I'm Bruce Jameson. There's been a lot of talk about using Bayes' rule or Bayesian updating in avalanche forecasting. I like examples, so I'm going to use one, a really simple example, to illustrate an application of Bayes' rule to avalanche forecasting for a ski area. Consider a ski area. There's the ridge, here's some start zones above the ski area, and here's the ski area boundary, and here's a study plot within the ski area. The forecaster wants to close parts of the ski area when avalanches are likely to enter the ski area from above. The forecaster has overnight records from the precipitation gauge in the studying plot dating back many years. The specific question in this example is, what are the odds of an avalanche entering a ski area from above after a night in which 10 or more millimeters of precip were recorded in the precipitation gauge? Let's define event A as an avalanche enters the ski area from one of these start zones above it, and event C is 10 or more millimeters of precipitation were recorded overnight in the precipitation gauge. Some of you who work in avalanche forecasting and control may have noticed that I used the word event differently. In avalanche forecasting, an event often refers to a single occurrence, such as a size 3 avalanche. In probability, an event recurs to any number of occurrences or data with a common characteristic, and we can define that characteristic however it helps us solve the problem. We want to know the probability of an avalanche entering the ski area after a night in which 10 or more millimeters of precipitation have been recorded on the gauge. This is written as the probability of event A given event C. Now we could look back through all the ski area records and actually find out this probability, but that would be a lot of work. Bayes' rule can make this easier. Next, I'll derive Bayes' rule. For those of you who are not interested, press the fast forward button at the bottom of your screen. Let's start with the Venn diagram, including all the relevant data. We have event A here and event C here. We want the probability that event A occurs given that we have critical precip in the study plot. That's the probability of this area in through here, these occurrences in through here, these days in which we have both A and C, given that event C occurs. So the probability of A given C is the probability of A and C divided by the probability of C. Now we can also write in the reverse, the probability of C given A is the probability of C and A divided by the probability of A. Now we can take this term here, C and A, and move it over to the left-hand side of the second equation, and we have the probability of C and A is the probability of C given A times the probability of A. Now, since the probability of C and A is the same as the probability of A and C, we can take the right-hand side of this third equation and put it in the first equation. Then we have the probability of A, given that C occurs, is the probability of C, given that A occurs, times the probability of A, divided by the probability of C. And that is Bayes' rule. So I've cleaned up the board to show only Bayes' rule. On the left, we have the probability of an avalanche entering the ski area, given event C, the critical precip. This term on the left is called the posterior. The next term is called the likelihood, and it's the conditional probability that is reversed. It is the conditional probability that's easier to calculate. This is called the likelihood. And the term in the numerator here across the top is called the prior. Now the prior sometimes keeps some traditional statisticians awake at night. The first reason for that is the prior is often taken from a different data set than the likelihood. So we're combining a calculation from two different data sets. Second, the prior is often a subjective probability, a probability estimated by experts. This is so common to use a subjective probability for the prior that sometimes Bayesian probability is used interchangeably with subjective probability. But we won't do that here because quite often the prior is also calculated from data. Okay, back to the example. The forecaster goes through the records and finds out on days with avalanches entering the ski area that precipitation is critical on 30% of days. In the denominator, there is critical precipitation on 20% of days. It is often useful, using Bayes' rule, to expand the denominator, in this case, into days with critical precipitation with and without avalanches entering the ski area. But to keep this example simple, we'll just stick with the 0.2 for the probability of critical precipitation. We could use data, that is records, to estimate the probability of an avalanche entering the ski area. But let's use subjective probability. The forecaster uses his or her experience to estimate that the probability of an avalanche entering the ski area on a random day is 5%. Now, plugging the numbers into Bayes' rule, 0.3, 0.05, and 0.2, we have an 8% probability of avalanches entering the ski area when we have critical precipitation. The forecaster decides, based on this 8% probability, that whenever there is 10 to 15 millimeters of precip in the precipitation gauge, she will close the bowls or parts of the ski area and send out control teams to use explosives to release unstable snow in the start zones above the ski area. Okay, what about wind? Wind speed affects how much snow arrives in the start zones above the ski area. We could again apply Bayes' rule as part of a chain or event tree. And what about wind direction? Well, we could also apply wind direction as yet another branch of the event tree. Sure, but there are limitations to this event tree approach. We may not have correctly broken down the problem into precip, then wind speed, then wind direction. When there are complex interactions between the factors, probability calculations become difficult or impractical. We are often better off to use experience and judgment to estimate the probability that we desire based on new information. So, in summary, Bayes' rule offers a way of calculating a numerical probability. Second, we can use a subjective estimate for the prior probability, and that's often quite useful because data are limited and being able to use a subjective estimate is quite useful. Third, Bayes' rule works best when we have a strong factor and we have some data for the likelihood. The ideas in this video are available in just about any book on probability. Stephen Vick's book, Degrees of Belief, offers an excellent source of Bayes' rule, but also a variety of means of making decisions based on limited data. Thank you.